Thank you very much for coming. How about we give our Gopher dancers a big round of applause? This is High Performance Apps with Go on App Engine. Thank you very much for coming. My name is David Symonds. I am an engineer on the Go team at Google, and I lead the technical development for the Go Runtime for App Engine. And as you might tell from my accent, I'm not from around here, I'm from the Sydney office. So here's what we're going to cover today. I'm just going to give you a brief overview of Go on App Engine. Hopefully many of you here have tried it out at one stage. Just give you a feel for where we're at and give you a bit of an overview of a couple of relatively high-profile apps that are using it. Then I'm going to introduce a motivating example for what we're going to use to explore some performance techniques for your app. And then the rest of the session, which will be most of the time, I'll be talking about those performance techniques in some detail. So why Go on App Engine? First of all, it's got the peanut butter and the chocolate in a great combination. Go compiles to native code. It runs really fast. It's a fantastic programming environment to work in. At the same time, App Engine is a fantastic platform as a service you can use to host your web app. It auto-scales. It's very, very low maintenance. I don't like getting woken up at 3 a.m. to fix things. I imagine neither do you. So if you're hosting on App Engine, we have people at Google who will wake up at 3 a.m. to fix problems when they happen. Combining these two together, we get the fastest runtime for App Engine. It starts really fast, it runs really fast, it keeps your instance hours down low, it's cheap for what it does, and you've got code running at full machine speed, so you can do sophisticated actual processing, not just serving text. So we first unveiled the Go Runtime for App Engine here at Google I/O 2 years ago. And since then, we've seen a lot of people adopt it. It's grown over time. It's supported more of the App Engine APIs. It's got better tooling. And we've seen steady growth and several high-profile users. And I want to talk about two that Google has done to give you a feel for what's possible. These are by no means hugely sophisticated apps, but they're kind of representative of things that are easy and natural to do in Go that might be a little bit harder in other languages, but they really show off the power and the speed you can get. First one is a front page of google.com turkey doodle from Thanksgiving 2 years ago. This is an interesting one because it was written by a Go newcomer. He'd never written any Go code before, but he picked it up and he got this high-profile app to launch in under 24 hours. So if you're thinking to yourself, I love App Engine, but I'm a Python or a Java programmer or maybe a PHP programmer now. What's Go got in for me? Maybe it's too hard to learn. This is great evidence that you can get from 0 to 100 miles per hour with not too much difficulty. Go's really easy to pick up. When this person built it, this app is doing some image compositing. So you can see it's rendering a graphic of a turkey with different feathers. You can see it animated from that link down below. But it's doing image work here. It's not just serving static images. It's doing sophisticated stuff. And this Go newcomer found that he could build this app relatively easily and get half the latency of equivalent Python 2.7 version. As you can imagine, launching on google.com homepage produces a fair bit of traffic. And this didn't miss a beat. And there's some more details of how well it performed at that link. Santa Tracker for last year was written in Go. And this was the component that kept track of where Santa was and informed the client-side JavaScript where to render Santa and how many presents he had delivered and so forth. It served a peak nearly 5,000 QPS, so 5,000 queries per second. This is also a very high-pressure situation. If things aren't going right, you can't just tell people, come back tomorrow for something like this. It's too late by then. We didn't make any children cry. And you can see down the bottom, we did this with under 80 instances. So this is a lot fewer than you might expect for this kind of query volume. So let me introduce to you GopherMart. GopherMart is a little sample app, and I'll have a link at the end of this presentation for source code for it. It's a bit of a silly app, but it kind of demonstrates enough of the features for us to discuss building a really high-performance app. So here's the situation. Imagine you are running an app to manage, or to run indeed, your GopherMart, which is your one-stop shop for all your Gopher needs. Your Gophers can come in, get their Gopher brand, their Gopher flakes, their Gopher litter, load them up in a cart, take them to a checkout, and then take them home, obviously. And the correspondence to an app that we're going to use is that the Gophers that are doing the shopping are your user requests. Each of your checkout Gophers, the Gophers processing each of those requests, is an app instance. And then there's a scheduler Gopher that's got a direct user request to app instances. A checkout Gopher can only deal with one request at a time. And checkout Gophers can be hired or fired in our Gopher Mart. But there is a certain overhead to this. This models how we deal with App Engine instances. You know, they take a little bit of time to start up. They're very quick to start up in Go, but still non-zero amount of time. And they can't be fired straight away. So our Gopher Mart has serious industrial relations laws. So you need to keep your checkout Gophers around for at least 15 minutes after they've been hired. But as in our Gopher Mart, our Gophers don't want to be standing in a queue with their Gopher brand. They want to get home and eat their Gopher brand, pour Gopher milk all over it, scoop it out of their Gopher bowls. They don't want to be standing in queues waiting for all this to happen. They'll get kind of grumpy if we take too long. So we're going to look at different ways of making our app really fly. I'm going to be looking at 5 different techniques. But before we look at any techniques, we have to understand the way that we approach high-performance apps. And it's very easy to fool ourselves into thinking that we know where the slow bits are. Whenever you're doing performance work, you need to first measure to understand where the slow bits are. There's no point in spending months of your time tuning and tweaking and caching and doing all kinds of things for one bit of code, yet that bit of code isn't your slow bit. So you need to measure first. It's also important to measure periodically. Your app will behave differently based on different request loads, different types of request processing, what you're trying to do in each request. So it's important to come back to measuring how fast it is over time, because it will change as you change your app. Even if you don't change your app, the infrastructure underneath will change over time as well, and almost always for the better. So App Engine gets better at scheduling instances to app servers. It will get better at getting the files to the app servers, starting them up quickly, and so on. Go got a lot faster. Just a few days ago when we announced Go 1.1, there was a major milestone, our second major stable release. That brought a lot of performance improvements. We got emails to the mailing list about people seeing their programs written in Go dropping from like 24 hours runtime to 9 hours runtime. So there's startling differences in every release of things. So you need to periodically come back to remeasure your app to understand what bits are slow and what bits aren't. The tool that we're going to be using to get a feel for how our app performs is called AppStats. And what AppStats does is it traces API RPCs over the course of a request. It measures the start time and the stop time, what these requests are doing, and also records a stack trace, so you can dig in through a web interface to be able to see where this RPC came from, how long it took, any errors that happened, and so on. And as you can see here, here's a timeline with time running along the x-axis of my first version of this app. Now, I wrote it as simply as possible, with no thoughts to performance, just simplicity. And you can see it's pretty slow. It's taking nearly 400 milliseconds. And what it's doing is Gopher comes up to the checkout. The checkout Gopher has to scan each item that was in their cart, and then emails them a receipt afterwards. This is a fairly modern Gopher Mart, so instead of just giving them print a receipt, they'll just get it in their email later on that day. So we're going to look at different ways of speeding this up. So I'm going to be covering 5 performance techniques today. These aren't comprehensive. There's plenty more that you can think of, and each one I'll be only giving a bit of a flavor for the depth that you can go into and to fully realize these techniques. But these should be 5 fairly representative techniques of how to tackle these kind of performance problems. First one to do is deferring work. Not all work needs to be done during the request. In our Gopher Mart situation, when the Gophers come up to the checkout and checking out their items, they don't need the email of the receipt right then and there. You know, they're going to take their cart out to their Gopher car, load up the Gopher boot with their Gopher brand, drive to the Gopher home. It's going to take them a little while. So the importance of getting the mail out to them straight away is not so important. And in general, a lot of web apps need to do things as a consequence of a request. but don't need to do them during the request. So this may seem like a pretty simplistic technique, and we'll get onto slightly more sophisticated ones shortly, but it's an important one to remember. Lots of the time you can forget that you're doing things that you don't need to be doing. The main ways that we're going to do this with the Go App Engine APIs, with the task queue API or the delay package that is built over the task queue API. And we're going to use this to shift work that it needs to do outside of the request scope. In our GoForMart situation, we're going to shift that slow mail.send call that took a large chunk of our timeline, and we're going to do that in a task that's going to happen usually very soon afterwards, but we're going to replace it with a very quick task queue.add, and we're going to use the delay package. And here's how the delay package works, in case you haven't seen it before. What it does is it wraps a function. You just go to try and invoke that function, and what it'll do behind the scenes is that it'll marshal the function arguments, store them in a task queue task, add it to the queue, and then when it comes back, it'll invoke your function for you. So it's a very, very simple way of dealing with task queue when you're doing it to defer work. So you can see at the top, 2 lines of my code from my simple version. There's a send receipt function invocation, and then you can see just the function signature of send receipt. It's fairly simple. All we have to do to use the delay package is import appengine/delay, and then we turn our send receipt invocation to stick a .call in there. Nothing else has to change there. And then we turn our function definition into a variable definition, and we just use delay.func, give it a name, and then we have our function body exactly as is. So there's no difference from what we were doing before. And you can see the effect that it has. It shrunk that mail.send call. It might be a bit slow. It might be waiting on the mail protocol to start so it can verify that it can send mail, spam filters, whatever it is. And it's turned it into a very quick task queue call. So this is a lot quicker, and then the mail will happen in its own task queue request. Second technique I want to talk about is batching. In our GoForMart scenario, it kind of makes sense that you don't want a family of 10 Gophers all going in individually, picking up their own box of Gopher flakes, walking up to the counter, each going through the process of checking them out, paying for them, and then walking home with them. It makes a lot more sense for one of the Gophers to go in by themselves, load up their cart with 10 boxes of Gopher flakes, and then check them out all at once. And again, this is a relatively simple technique, but it's often overlooked. And this would be using API calls like get multi instead of get or put multi instead of put. And usually they're a little bit more overhead than just a single call if you've only got a single object. But a lot of times you're dealing with multiple entities, and so they can be a lot quicker because you only have one lot of the RPC overhead instead of n. So here you can see the code that I wrote for the simple version. You can see that it's just sitting in a loop, and for each key, it goes and fetches the item corresponding to that key from the data store, deals with any error, and then just builds up a slice of those items. That's obviously very simple to understand and to reason about, but it's slow. And here's what we do when we batch it. Instead of a loop where we're doing each data store call, we use data store.get multi. We tell all the keys to go and get, and then it returns all the items for us. And you can see, in this case, the task queue call was very luckily short. But more importantly, the data store.get call turned from 5 sequential calls into just one short one. So we've already cut down our program's request processing time dramatically. Third technique I want to talk about is caching. And I'm sure many of you have cached things in the past. And in our GoForMart scenario, this would be like a checkout Gopher remembering that for certain fresh fruit, which might not have barcodes and they normally have to look up a booklet for, they just remember go for berries, 361. Go for bananas, 492. They can just remember these things once they've been running for a while, and they can be a lot quicker. But the first layer that I want to talk about is data store. And data store is a great storage system. It's very fast, it's very reliable, it's highly scalable, but it can also be used as a cache. So your program might be doing expensive computation work, might be compositing images. It might be fetching a request via URL fetch from a remote server that's slow. It could be doing any number of things outside itself that it has very little control over that can be quite slow. We could stick those in the data store, and then all of our app instances can check the data store before trying to do that expensive computation or remote fetch. One thing even faster than data store is Memcache. And as opposed to data store, where a small get might take 20 milliseconds, thereabouts, Memcache can do it in about 1 millisecond. So it can often be 20 times faster for small workloads. And it's great. It's shared across all your instances. You know, one of your checkout Gophers needs to look up the code for Gopher berries, stores it in Memcache, and every other checkout Gopher suddenly gets the benefit of that caching. You need to remember that unlike data store, Memcache is not guaranteed to hang around. It's not a persistence storage system, so it could get flushed anytime your app has been using Memcache too much, or the App Engine infrastructure moves your app to another data center. So you can't depend on it being there, but it's a great way of keeping hot used data at immediate access. Third thing to use, and something that might be quite foreign to in particular Python programs, is using local memory. Your app is running as a program on a real machine, and we can easily forget about that with our abstract notions of the App Engine setup and instances and requests, and it all feels very abstract, and we forget that they're programs running on a machine, and that machine has memory. So we can use local memory in your app instance. It would just be sticking things in a global variable, for example. And that's even faster. That's 3 orders of magnitude faster than Memcache will usually be for small amounts. It's even more fragile than Memcache, though. It's not shared across instances. So if one instance gets shut down because it hasn't been receiving enough requests or it's not needed, that memory will disappear. But it's an important tool in your tool belt when you're caching things to use local memory. It can be heaps faster than Memcache, heaps more reliable, with the proviso that it will disappear. The third technique I want to talk about is concurrency, and this is where Go really shines. And this is where it really excels as compared to other runtimes. Concurrency is where you can decompose what your app is doing into independently executing things. So even though Go on App Engine is, at the moment, bound to a single CPU thread, concurrency allows you to decompose your program so that you can write very simple chunks of code that will run concurrently, that might not run in parallel, but while one is blocked on an API request, another one will immediately start running. And in our Gopher Mart scenario, this would be as if a checkout Gopher needs to get a price check on an item and then can immediately start scanning the other items. You know, if you walk into a regular supermarket, you don't see somebody waiting for a price check and then just standing there waiting, getting the price check back and then doing the other items. They go on and do more things, and so that's concurrent work. So let me take a bit of our code from our example app that was poorly written by me, and let's make it better and faster by using concurrency. So here might be a little chunk of code that needs to look up all the entities of two data store kinds. In this case, we have a list and an item kind, and we want to get all the items of each. This is a straight line code, and it's very slow. If each query takes a certain amount of time, the total time to run this bit of code is going to be the sum of the times. It'd be much, much quicker if we could run them in parallel. And since most of your web apps, most of all web apps, tend to be bound waiting on API calls to come back from various other services, this is an easy way to speed up most requests by doing things concurrently. So here all we've had to do is kick off 2 Go routines to run these queries, and they'll be independently waiting, and then we're using an error channel to signal when they're done. Hopefully it'll send back nil if there's no error. And then down at the bottom, we just wait for both of them to return. This means that instead of 2 requests summing together, we now end up taking time roughly equivalent to the maximum length of either of them. So that's going to be strictly less than the sum in any reasonable scenario. So this is a very simple flavor of concurrency in Go. This is far from sophisticated. So I'll commend to you my colleague Samir Arjamani and his talk this afternoon, where he'll be talking about some advanced Go concurrency patterns. So if this kind of thing sounds interesting to you, and it does to me, get along to that talk. The last technique I want to talk about is fourth, fifth. The next technique I want to talk about is controlling variance. And in our Gopher mart, we have a 10 items or fewer queue, but occasionally a Gopher comes by when they've got a few more than 10 items, if you know what I mean. And while most Gophers might take a millisecond to process, 1 in 100 might take 10 times that. It might take 100 milliseconds, for example. And this is a very common thing. It could be due to the request. So in our Gopher mart situation, it might just be the occasional Gopher with a very, very big cart full of items, whereas most carts only have a few items. But it can also be due to the infrastructure underneath your app. And the App Engine infrastructure is great. It's highly scalable, it's fast, it's dependable, it's very reliable, but it's not perfect. Occasionally you'll be doing data store requests and they'll be going 20 milliseconds, 25 milliseconds, 22 milliseconds. Be really reliably quick, but then a small fraction of it might take half a second. And the consequences of this kind of variance can cascade through our system if it's sophisticated. If your app needs to do several things in a sequence where each one depends on the results of the previous one, such that these things can't be done concurrently, then a variance in one affects the whole pipeline, and the perfect storm of variance affecting all of your items in this sequence will blow out your request time hugely. Variable requests also make scheduling a lot harder, and this is something that I haven't really touched on much, and I won't go into too much detail. But the App Engine scheduler needs to take a guess as to which App Engine instance each request will best be served by. And it's got to balance across them. If it's getting too much traffic, it'll start up new instances and so on automatically. But it needs to usually, for the most part, take a guess as to which instance will be idle the first, and so I can add that request to that App Engine instance's queue. The less predictable your request handling is, though, the harder it is to do that kind of prediction. So if there's variance in your request handling, the scheduler, though it is great and highly sophisticated, will start to make mistakes more often. And so you might get your instances being a bit overbalanced, one handling 100 requests for only 2 being handling by another, and so on. So it might make mistakes there. And this will lead to you requiring more app instances, more instance hours, which will lead to a higher bill if you've got billing enabled. So what we want to do is control the variance of our requests. We want to put an upper limit on how long we're going to spend doing certain operations. I'll point you at this paper published in the ACM by two guys from Google. This goes into a lot of detail about some techniques for controlling this kind of variance, in particular long tail latency, and it's geared around machines in a data set doing server processing, but the same techniques apply to web apps that are processing requests as well. So I'm going to discuss just one way of doing this. So I'll point you to that paper to go into more detail. Storing in Memcache is usually an optimization. So as I mentioned before, Memcache is not perfect, and it won't necessarily guarantee to hold your data. If you need guaranteed data storage, you need to store it in something like Data Store. But Memcache, as a result, is usually an optimization. And optimizations by their nature are usually optional. So what we want to do is, in our request, we don't want to spend huge amounts of time, unlimited amounts of time, on these things that aren't strictly required. So in our Gopher mart scenario, we might be doing a bunch of request processing, and then we might want to store those fresh fruit items that we've looked up out of a booklet in Memcache, but we don't want to spend infinite amount of time doing that. Memcache might be briefly down, or it might be running a bit slowly, or whatever it is. So we want to cap the amount of time that we're going to spend waiting on it. And here's the first approach that does not work. In our request handler, we might just kick off a memcache.set operation at the bottom in its own goroutine. And we think, that's great, my request will immediately return and Memcache will do its thing behind the scenes. But the problem here is that in the App Engine model, the scope of your context objects are bound to the scope of the request. So any API calls have to be done while the request is still going. And as soon as the HTTP handler returns here, your context will be invalidated, and any outstanding API calls will be cancelled. So we can't do this. Here's what we can do. We can, again, kick off the Memcache operation concurrently, and then we use a done channel. And this done channel is going to be signaled on as soon as that Memcache operation returns. And then down the bottom, we use Go's concurrency primitive called a select block to wait for one of two channel operations to happen. The first one, if the Memcache operation finishes, we go through, there's nothing in the select body, so nothing's going to happen, but we'll just immediately return from the HTTP handler. So in the likely event that Memcache is its usual quick and speedy self, this has no overhead. The second case, though, is if we end up waiting a bit too long. And Memcache will usually be 1 millisecond, 2 milliseconds, depending on what you're doing with it and how much data is being sloshed around. If it takes more than 3 milliseconds that we've decided we want to wait for, time.after will signal on the channel that returns after 3 milliseconds. So at that point, if Memcache takes too long, that second channel will be signaled on, we drop out of the select loop and return. And at that point, the Memcache operation will be cancelled, it will fail, it will go away, and we've returned to the user. So using these kind of primitives to time out waiting for things that are optional is a useful technique to ensure high performance consistently. So here's an overview of where we went. We started off with a very poorly written app on my behalf that did very simplistic code. It just did a sequence of data store operations and then a mail.send and took nearly 400 milliseconds. Just by applying two of the techniques that we did today, we got it down to only 70 milliseconds. So a dramatic speed up with very little work. Once you've got experience with that, these kind of transformations will take 5 or 10 minutes. So it can be very quickly done. So let me sum up what we covered today. First thing is to find the performance bottlenecks in your code. Don't rely on your own intuition, because your intuition will fool you reliably. And even if your intuition is correct one day, it might be incorrect down the road. So important thing to note is to measure and measure and measure and keep coming back to measuring to understand your app's performance. Then the 5 techniques that I covered: deferring work, moving work that doesn't have to happen during the request out of the scope of the request, probably by using task queue or the delay package. Batching, so doing multiple operations in one shot. Caching, so memoizing data, might be in the data store, might be in Memcache, might be in local memory, or might be even in other places that I haven't mentioned, so that you can check them later and speed up those parts of your app. Concurrency, so decomposing the work that you're doing into independent pieces that can be combined. And finally, controlling variance to cut off the long tail of latency so that your app requests can be consistently quick rather than very, very occasionally taking a bit too much time. So finally, here's a bunch of links to the Go project in general. There's a heap of documentation on there. You can download Go, try it out online. The second link is to the Go on App Engine docs. The third one links to these talk slides plus my really bad source code for the Gopher app and its revisions, and then to the app stats package that was written by Matt Gibson, who might be here. He did really good work on that. There's more Go sessions coming up later today and tomorrow, so get along to that. In particular, I'll be at the office hours downstairs, this level, at the Cloud Sandbox if you have any particular questions about Go on App Engine, whether performance or otherwise. So come along and have a chat. So with that, I'll thank you for coming again, and we can take questions.
Can you hear me? OK.
Hi.
So I've been using Go for a while now, but I haven't used the App Engine yet. So a quick question on the control variance.
Yep.
Instead of trying to set it in Memcache right there and there, could you not put it in a global channel and do a select on it with a timeout and then handle it outside?
In a global channel? You mean like in a global variable?
Right.
Yeah. Yeah, you can store it there right away. The downside of that is that it'll only be used for that app instance. So the memory for each app instance is only accessible to the app.
No, that wasn't the question, sorry. So the operation of setting it in Memcache, instead of doing it in that handle, could you not put it in a channel and then pick it up from there with a worker to set it in?
Yep. You could. The only way to make API calls is during a request. Okay. So you can't kick off a Go routine that does its own thing independent of requests. You could put it in a channel and in a later request pull things off the channel and do it at that point, or use a task queue or use backends to do that kind of thing. Yeah, that would work.
Okay, thanks.
Yep. One from this side.
Hi, Nelson from Mailabs. Can you comment on a couple of techniques people are using to make Go applications more efficient in pricing compared to Java and Python?
So I mentioned that Go apps get compiled to native code, they're binaries. That results in them starting up really quickly. So every time a new request starts coming in and the infrastructure decides to spin up new requests, it'll be a lot faster to load. It's just got to run a single program. It doesn't have to start with a virtual machine, page in a bunch of modules or whatever it is. So it can be really fast to start. That means that that single instance starts up quickly and immediately can start doing work. If you suddenly get an onslaught of traffic, in other runtimes, you might have to start up a bunch of instances. That'll take a little while, but then they can deal with all the traffic that's coming in. The second main way is that you have a lot more control over the memory that you're using. Go is a very hands-on language. It gives you a lot more control over things like memory layout and so on. So you can allocate a slab of bytes, and you've got that slab of bytes. You don't have any overhead from that. So using those kind of things, if you're intensively using your application instance's memory, you can fit a lot more in, say, an F1 instance than you can in, say, another runtime. Yeah.
Why did you use a buffered channel in that last example?
Good question.
Is that so the Go routine dies?
Yeah, I use a buffered channel in case the timeout happens. So if the timeout happens, nothing's got to be reading from that done channel. So if the timeout happens, nothing will be reading from that buffered channel, which means when the Memcache call does return, it'll block, unless I buffer it. So I buffer it so that if that timeout happens, the Memcache can return, still do a channel operation to a channel that will just disappear, but then that Go routine will exit and won't be hanging around.
So there could be a memory leak if you don't do that?
You'd have a Go routine leak, yeah, there would be a memory leak in that case if you didn't have a buffer channel.
It's not tied to the parent channel, or the parent request?
No.
Okay.
No. Yep.
I have a few short questions. Thank you for. NDB has caching built into it. Is there any plan to do that for Go?
Yeah, there's a couple of external packages that have been written that provide an NDB type layer. I can't remember them off the top of my head, but they're out there, and I can look them up if you want to ask me at office hours.
Thank you. And also, you seem to imply it's only tied to one CPU, right? But Go is really powerful with multiple CPUs. You seem to imply that there's a in the future that won't be the case?
So each of your app instances runs CPU bound on a single thread. So while it's doing an RPC to do a Dart fetch or whatever, it'll switch to other things. So it's got concurrency in that respect, but we only have one CPU thread running at any one time.
But
for now.
Yeah, but it could change in the future.
Yes.
Right? Yeah.
Yes.
Thank you. Thank you.
Yep.
Python and Java runtime has a unit testing package with App Engine APIs.
Yep.
Now Go has no unit test package for App Engine APIs. Do you have any plan to?
Yes, we realize the testing story for Go on App Engine is weak, and we have plans to improve that in the near future.
Thank you.
Just a question on the multi-threading side. If I take an instance with 2 cores, what's happening there? One of them sits idle all the time?
So the instance classes are based on virtualized CPU gigahertz rather than number of cores. Sorry, I'm not sure off the top of my head what it would do if you were on 2 cores in that instance. It's possible that you would run multiple instances on that machine instead.
Thanks.
Yeah. Any more questions? Yeah. Okay, thank you very much for coming.